Hello, everyone. Good morning, good afternoon, and good evening to viewers from all time zones. I'm Parul Saraf, Customer Engineer for Infrastructure Modernization. Now, let's welcome one of our readers, Mr. Rajesh Randas, who is the Head of Customer Engineering, North Enterprise and Corporate Accounts. So Rajesh comes with 27 years of experience in areas of customer engineering, implementation, support, development, and functional areas in manufacturing and IT. Knowledge and experience of IS, PaaS, and SaaS. Managing high-performing team in the areas of data management, application development, integration, analytics, and business application. Hiring awesome team, coaching customer engineers, new solution development, building trust with customers, and build influential relationships for our top customer have been key areas of Rajesh's work. Over to you, Rajesh.
Great. Thank you, Parul. Thank you very much. Let me start by giving you my point of view of what's happening. See, over the last 2 years, there are 5 important events that are happening that is accelerating the cloud adoption. First is around digitization because of COVID. Second, there is pressure on fixed as well as IT budgets. It's a very, very important part. Third is work from home has been like a default stuff for everyone. Fourth one is about technology, whether it is 5G or LTE or some other technologies which are evolving in nature. And finally, around digital sovereignty requirements, where every country is saying, I need the data in my own country. These are the 5 areas that we are seeing that are accelerating the cloud adoption. Now, if you look at what we are doing, we want to work with organizations to help digitally transform their business with our best infrastructure, data AI, industry solution, and the expertise we bring to the table based on our years of experience. So the question is, how are we different from others? We believe we are different in 3 areas. Firstly, from a technology perspective, whether it is mobile first, mobile only, APIs, AIs, data, or focus on the next billion users, we have done it all. We have the technologies that we have consumed ourselves that we are giving it to you. The second important thing is around pricing. It is around pricing efficiency and differentiators there. And the third important aspect is around leveraging the best of Google, which is to help foster culture of innovation across the enterprise. So these are the 3 things that we help us differentiate in the market. So what does it mean when we say leverage the broader Google ecosystem? Whether you're doing shopping, whether you're doing payment, whether you're actually doing maps, or organizations want to market, these are the areas that Google has been working for decades now, which is helping our customers drive their digital transformation process. Now, if you come to Google Cloud per se, we have 4 ways that we reach out to our customers, 4 important solutions. First one is around infrastructure and application modernization. Second one is around data and analytics. The third one is around AI and ML. And the fourth one is around industry solution. So what do I mean by that? When we talk about infrastructure, we have built infrastructure at scale. Whether you're running everything just on GCP, or you're running on multiple cloud or on a hybrid cloud, whether it's on-prem or cloud, we have solutions that will help you manage your high performance and global scale requirements. Second one is we have built in the required infrastructure, whether it's around networking with having the largest network globally, okay, of any provider. Second is creating compute, wherein we have built in our own security by embedding our own chips. And third, helping you create applications that can run on multiple clouds or multiple hybrid environments without you having to refactor or redevelop that entire thing. And in this area, if you see, whether it is compute storage network, we have been able to differentiate with our AI for our customers. On the application modernization space, we have what we call cloud application modernization program, okay, where we actually work with customers to provide you with the best practices in terms of app dev process, whether how do you actually build applications, how do you create uh, multiple applications, you are able to create multiple scripts onto it, able to run DevSecOps as part of your app dev process. Why are we so comfortable with this? Because that's exactly what we do. Google creates like 4 billion containers a week. And from an app dev process, every day there are millions of changes that are affecting so many of our products. Okay, that's around infrastructure and application modernization. If I look at data, we understand data, whether it is structured, whether it is unstructured. Okay, we understand data really well and have the ability to unify into a native warehouse, whether it is around data lake, streaming, and the, on top of it, we help you build your AI ML algorithms to dramatically look for insights into the data, whether it's around fraud and errors, whether it was about looking at segmentation of customers, we can easily do it. Some of the things that we have done that has really changed the game is to make it super easy for business users to actually query on data. So instead of everybody having to write SQL queries or any other similar queries, you can now look for information very similar to a Google search. So you can actually write in an English language. Behind the scene, the system will actually convert that into structured queries and give you the desired result. So that's how we are getting data management and analytics to you. But if you look at our portfolio, we have the largest portfolio in the market, whether it is in-memory databases, structured and unstructured one, whether SQL, NoSQL, or relational database. We have solutions that Google has created on its own, but also support solutions from our strategic partners, whether it is Redis, MongoDB, Elastic, or any other organization. Many of them are built and managed by Google, which will help you scale and deliver the applications globally. Okay, that's around database. The third important aspect is around AI/ML. When we deliver AI/ML, we have done two important things. One is, can a person start using the AI algorithms directly into their applications? The answer is yes. We have actually created what we call APIs, whether it is relating to vision, whether it is relating to translation, whether it is relating to speech to text or text to speech, or whether it is relating to documentation. These APIs have been exposed so that customers can add that as part of their DevOps process and get the AI ML directly embedded as part of their solution. One of the interesting use case that I have seen when I was getting onboarded into Google was use of Vision AI, where I had to take the download an application, take a selfie of myself, take a picture of a document, which is government issued document, PAN card, Aadhaar, or stuff. And then behind the scene, the system would actually collate and figure out whether the person who is claiming that he is, for example, if I'm claiming I am Rajesh, is matching with the identity that is provided by the government. The second thing that we did from an AI/ML perspective is what we call AutoML, where you can actually give the data and we will tell you what is the best algorithm to use. We will apply multiple algorithms, we will tell you. So almost with zero code, you can start your AI/ML practice. That's very, very powerful, and we have seen customers really use it. And finally, it's around industries. Industries, whether it is retail, healthcare, financial services, media, manufacturing, or public sector, we have created solutions using our leadership in AI/ML to transform core industry processes. Okay, so if you look at what is happening globally, if you see, most of the top 10 customers are already using Google Cloud in some form or the other. Okay, whether in media, whether in manufacturing or financial services, you have a host of customers who are using our solution. With that said, I'll actually want to again thank you for spending your time with us, and happy learning. Thanks. Bye-bye.
That's a great kickoff. Thank you, Rajesh, for your message to the YouTube citizens. We are now getting into the first tech session. Today, I'm bringing Reva Modi in front of you, who will help us select the right database for modernized applications on Google Cloud Platform. Reva Modi is a principal architect focused on Google's customer in the banking industry. I can't wait to hear the words of wisdom. Over to you, Reva.
Everyone, this is Reva Modi from Google, and I'll be sharing some of my experience and my recommendations around choosing the right database for modern applications with you today. I hope it's going to be interesting for you as a journey as much it was for me to build this content for you. Long before, when all of us used to go to work, you would see rows and rows of files. I hope you don't see that today. And if you looked at it, it was a way of organizing information in subfolders, and each of our profiles would then go onto a form, right? Thankfully, this is not the case anymore. For the last 30 years, relational databases have become systems of record for all enterprises. So what have we actually ended up doing? We're pretty much mimicking what the real world used to do. So the database now becomes, or the schema becomes what used to be the file rack. And a table essentially organizes information like the file does. And each of our information then becomes a row. We then need a quick way of accessing it, which is known as the index, very much like you would your phone book, right? So essentially an RDBMS, the way it organizes and stores information is pretty much how the real world information is organized. What kinds of things are stored there? Employee records, attendance, salary, and department related data. How does it look like inside a relational model? Pretty much what you would expect. An employee belongs to a department, a certain salary grade, has a certain gender, and they have associated master data like their degree. What comes now is the 1990s now change into a huge internet explosion. The type of data that we have to deal with is a lot more varied than transactional data. The speed or the amount of data that users are generating also changed, and the reams of volumes. So we went from a world that was really structured to a completely unstructured world. Think about how blogs are just blank pages on which a user may choose to write anything they want, upload a video if they wanted, or attach a sound file. How can an RDBMS that was clearly defined for very, very structured data in rows and columns now deal with data that is neither consistent in what it contains, nor does it have a similar format? The other complication is the sheer volume at which this data is generated and the velocity at which it is to be stored. The older technologies, or the ones that actually helped us make our transactional systems robust, did it by vertical scaling, which means you added more resources in terms of RAM or CPU to a box, as we call it. Whereas now, the need is to be able to store data at a much more inexpensive way. And why do we need to do that? Because all of the startups and everybody that is started to function in the unstructured world were doing so at a budget at which they were experimenting. So commoditized technology or commoditized hardware and scaling it using commoditized hardware became the need of the day. If we look at what were structured databases providing us, they were providing us consistency for use cases which were prevalent at that time. A banking solution where a credit and a debit must be consistently stored, or that entire transaction has to be executed at one shot. You couldn't have a credit from one account and then come back sometime later and see that that is not holding, right? So transactional consistency was one of the most important use cases that this database solved for. But do you really care if your blog post was 10 seconds delayed, or if you hit a like and it suddenly disappeared? It is not of the same criticality as having your bank account debit going wrong. So what did these databases choose to do? They chose to favor the speed of writing and the speed of reading over consistency. If you were to be very, very theoretically correct, they were addressing a paradigm called the CAP theorem, where you could either have high availability or you could have high consistency, given that you were putting your database data out in different partitions or different servers, right? So structured, vertically scaling and consistent; unstructured, horizontally scaling and extremely fast, both for volume and velocity. So what does it take now in this modern day and age to actually save the world? You have transactional systems being built on very, very solid RDBMS technology, but the other use cases actually need four or more other databases to actually solve the problems. These go along as key value pairs, column store databases, document databases, and graph databases. We're going to spend the next 20 minutes learning about the use cases under which you can leverage these technologies. What is NoSQL? NoSQL doesn't mean no, it means not only SQL. And why do we do that? When these databases came up, they solved a point solution of fast retrieval of a different type of unstructured data. They facilitated the use cases of the consumer, not just of storage, right? If you look at what SQL was doing, was two things amazingly well. The first was organizing data in a consistent fashion in rows and columns, allowing us to put in referential integrity constraints, allowing us to have transactions, and using SQL query language, retrieve the same consistently no matter who was building the applications with what database at the backend. When the NoSQL world started to explode, the querying languages varied a lot. As time has passed, each of these patterns of databases also support SQL query language access. So what has happened is you can query this data in the same fashion that your code is used to querying a SQL database, except underneath the storage is optimized for a certain kind of retrieval. A double click on key value pairs, right? A key value pair is essentially like your contact book. You're storing a name, and against that name in your mobile phone, you're storing additional data around the person's number. You may store their email address, you may store their additional WhatsApp contact, or the organization to which they belong. So key value database structures allow for you to retrieve a whole record or a whole bunch of data given just one key value. Typically, you will see this use case a lot in situations where you have internet scale applications who need to manage session information. So you have user preferences, and these are captured both explicitly when we set up our preferences in the application, or they may be captured by the application given what your user ID profile is. All of user data, user session data, and preferences are stored in what we call as caches. These caches essentially allow key value pair retrieval, and these are extremely quick for reads, and they're heavily accessed. So the ratios typically could vary as much as 100:1, which means you write once to this, but you will be reading this data over 100 times. We then move over to another style of storing a key value pair data. These are wide column store databases. Here, the scale has completely changed. We're talking about millions and billions of rows of data across thousands of columns. The advantage or the special use case that these solve for are around aggregating events, aggregating logs. And how do they do that? That's because they are essentially time time series databases. They are storing timestamps along with as part of your key. And so you can progressively aggregate or filter through or process data in a time series. Document data store, unlike the name, are not about PDF documents or Word documents. What we are referring to here is, instead of rows and columns, we're referring to JSON objects. What does it contain? An entire object. So if you were to store a particular set of information whose underlying properties tend to vary, for example, a product catalog. In a product catalog, all you know is categories, you know the specific product ID, but the attributes vary greatly between 2 or 3 different kinds of products. And then when you look at the scale of some of these e-commerce providers, thousands of property variations occur. Why is this a better way of storing such data? When you retrieve it, you will process it based on the attributes that you're receiving. You don't need to bloat the database with additional attributes or columns. How do you design a schema beforehand when you don't know what attributes will evolve? So what this style of storage allows you to do is 2 things. It allows you flexibility of having multiple attributes and retrieving each of these as different indexes. So what do I mean by that? If I want to search in a catalog by age or by size, this attribute could be present across multiple records, and you could retrieve it instantaneously just as if you had actually named that particular object. And that's the difference between document store as well and your relational store. An interesting variant and a very difficult to use technology is the graph database. Here, the relationship between 2 nodes is stored as a primary data. What do I mean by that? Imagine storing social network data in a relational format. You would end up designing columns and you would retrieve 16 rows before you could figure out that a user is connected to 9 other users. Instead, a graph database stores relationships along with nodes. So what you're retrieving is the entire network rather than retrieving and traversing this row by row. So when I look at relational and non-relational worlds, I think about 2 factors. One is that relational databases allow for relational semantics, which is SQL. And on the non-relational world, it may or may not support SQL. Relational is designed for strong consistency, and non-relational is designed for eventual consistency. What does that mean? If I retrieve the data right now, a relational database will consistently return within the same micromilliseconds the same value. Whereas in a non-relational case, because we store multiple copies of the data, because of the way the data is structured, you may see some stale data come through. Is this visible to us in real-time use cases? No. But from a design perspective, that's the compromise or trade-off that has been made. From a relational perspective, if you had to do availability or a high availability, what you have to do is configure multiple nodes and you have to fail over. Whereas in a non-relational case, your availability remains high because it's usually designed as a bunch of master-slave configuration where each server is equally participating, right? So it scales because there are multiple servant nodes. And when you look at that, vertical and horizontal scalability, we are thinking expensive hardware, resources through RAM, resources through compute. Whereas in the non-relational case, you can scale horizontally, which means that you can continue to add nodes to this cluster that are not necessarily all high compute, high memory nodes. See that? Okay. Now, what if you're facing Thanos? Can all of these put requirements, which is I want to query and have consistency in my database. I want to do it at internet scale like the NoSQL databases do. I want to have horizontal scalability like the NoSQL databases do, but I want the convenience and the predictability of working with a SQL and RDBMS style database. Who needs such a use case? At Google, When we are working with the world's information, the scale at which we operate required us to actually look at this use case much more deeply. And we've taken and released that particular technology now as something that enterprises and end users can leverage. I'm talking about NewSQL. What NewSQL is doing is solving the problem that the relational ones wanted to do, which is provide a consistent way of persisting transactions, along with the same high availability and horizontal scaling of a NoSQL. Essentially, we are now able to provide infinite scalability without compromising on performance, without compromising on the ease of use, and ensuring that you get consistency, which means if you are now building a banking use case and want to do it at the scale at which you are having millions of transactional requests like you do with digital payments, you could look at Spanner. It would scale horizontally based on the load that you fire at it. It would be available across multiple clusters and multiple zones without you having to invest any time in managing the hardware or spending time scaling up any of this. So if I were to summarize, a great customer experience essentially is your front-end application, but enabling behind that are databases. And that is the transaction pathway that I want to talk about. We're going to now look at all of these use cases from one particular scenario. Meet Reena. So if I were to spend a day with her, she goes to an e-commerce website. She's looking for a mobile phone today. She then walks up to office and marks her attendance. Remember, she's a specialist who works in an IoT lab, and she will head to the research department. She herself is building a custom application that maintains the life cycle of devices. She then probably spends some time playing a game, and definitely checks in at the end of the day with her friends on social media, right? Where we will go with this journey today is to tell you that when you're designing an application, you don't need to use only one database. It is a world of polyglot, which means that we have use case specific options and patterns that are now considered fairly mature to be used in very, very high scale scenarios. So we look at a Google Pixel phone and you're hitting a search. Ever wonder how these are able to actually retrieve even as you type, right? What are the kind of technology that you would have to put if you were to do search like behavior? If you try to do this using relational technology, trust me, you have no way of meeting this performance or the functional ease of these use cases. What we do is actually use what we call search databases. Search databases are special. Under the hood, all of them have document style storage, right? So they are storing in JSON. What they do very, very effectively is provide you a way of indexing, wildcard search, as well as different patterns of fuzzy logic for matching secondary set of search results. Google provides Elastic Cloud, a managed version of search. The next thing that you do is place this item on your cart. If you look at the cart itself, what does it have? It is indexed on the SKU, or what we call what you're trying to buy, right? And it stores all the other attributes as part of the order. If I were to model the cart, I would put it in a persistent cache like Redis or a Couchbase. This allows for two things. It allows you to retrieve the cache really, really fast, so that when you're walking through this experience, you know that for this user, I have this SKU and here are all the properties that I've actually built in the cart. And you can do this at scale when all of us have big $1 billion aspirations to book something, right? Why persistent? Because the cart, otherwise a cache will typically expire your data, right? Whereas a cart needs to be persistent across sessions. In Google, we provide Cloud Memory Store, which under the hood essentially has Redis as a provider engine as well as Memcache based on what you want to choose. Payments, you're back definitely to a space where you want transactional consistency. You are also going to have a lot of relationships in terms of validating and verifying based on user ID, based on transaction type, based on merchant, right? So what you're doing at real time, your use cases require you to have a very, very clear relationship and consistency across transactions. In this case, your options are there for MySQL, PostgreSQL, SQL Server, and on Google, you can look at Cloud SQL, which under the hood supports managed MySQL, Postgre, and as well as MS, Microsoft SQL. So what have I done so far? I've searched using a search DB. I have got a fully built out cart, which is right now immediately retrievable to me from a Redis cache perspective. Now the site is giving me recommendations. Remember, recommendations are far more difficult than a search, which goes after a single index value or a multiple set of index values or a card. Here, somebody is processing my preferences, somebody is processing across to what's in the inventory and then making these recommendations. So typically we would use something like Janus Graph with Bigtable or Cassandra, which are time series column store databases. Remember that she then walks up and marks her attendance. Again, this is a case where you're dealing with an ERP system or an HR system. The HR system is all about organized data where they're trying to retrieve whether this person is entitled to certain leaves, or they are processing all of these queries, ensuring that when they actually deduct time data or transfer data over as records to payroll, all of this has to be a consistent record. I'm almost tempted to say you could, this looks like time series, but actually the volume of data that you will get on an attendance swipe is not as high as that to warrant a Bigtable kind of or a Cassandra type of use case. You're much better off with a SQL database because you're going to store structured data and use it in a structured fashion. So options, again, MySQL, Postgres, Cloud SQL. In the IoT lab, she is dealing with millions and millions of data points that are streaming through at a very, very high rate. In this case, storing these data points in a time series database means that she has very low latency, high frequency writes happening in her database. The options here are InfluxDB. At Google, we store all of this kind of data in Bigtable, and that's available to you as part of Google Cloud. We're back to what she does at her job, which is work with a catalog application. Remember, we early on saw a document store, and this document store helps her how? Each of these devices have very different attributes, but services and microservices that you're writing are going to want to provide the same sort of interfaces, which is you're going to look for a description, you're going to look for a UID. But below that, there are a lot of variations at the individual device level, which is supported in a document store. You can index it either by location. You can very easily look at the properties that you want to retrieve on for purpose, right? What happens with a document store is your reads become extremely friendly because you store the entire object and its child objects together. And typical patterns here will be MongoDB, CouchDB, Firestore, and MongoDB Atlas. At Google Cloud, we provide two options, Firestore and MongoDB Atlas. Firestore has another advantage. It works in an offline mode as well. So when you're building a mobile application with, say, the SDK, you're going to be finding a bigger advantage using Firestore because you can work, synchronize this once your user is actually connected to the internet. She then plays an online game, and now we're talking about millions of users wanting it in a competitive fashion at the millisecond level. The leaderboard the concurrency required in a multiplayer game is requires a very different treatment of the same data. In this case, you can either use a document store like Mongo, which is extremely responsive to both read and write, or you can use a horizontally scalable solution like Spanner, which is a managed SQL, which means that your coding, the way you structure everything becomes much easier. Not only does Spanner support petabytes of data, it does so at the same latency, right? There is no deterioration in the retrieve for all of these million users that are logged in. The second advantage is we look at multi-regional deployment, which means that you can have players spread across multiple countries and the latency requirements have to be met for each. In that case, managing something that you will provide or provision becomes much more difficult than using something that is out of the box, scalable across multiple countries and provides 5 nines of availability. Last but not the least, there are many different patterns you can have of database usage, even when you're doing social media. But we will take one in particular, which is the graph of me and my friends. How do you actually operate such a query? If you try to do that with any other structure, it would take much longer, and you would always have to enhance that as the number of relationships that you were trying to maintain grew, right? And this would not scale well. So we use graph databases in this case, whether it's a Neo4j or a Giraffe. The idea being we need the relationship to be a first-class citizen of the design. Okay. Then why are we talking about databases on the cloud if we have so many options that you can manage yourself and deploy? Questions that I ask are, what are the varieties of databases do you want to use today, right? And when I say what you want to use, I mean, think about yourself as a developer, think about the team that is going to manage these databases, think about all of the DBA activity that goes on when you start to build out polyglot applications. How are you going to meet the scalability requirements of your critical apps, right? Are you going to continue to invest into more hardware? Are you going to be able to provision these things in time? Remember, crafting a high availability and DR for these databases is a non-trivial exercise. You will also have hardware refresh cycles, because as you continue to upgrade some of these licensed products, they are going to demand more later versions of the CPU and RAM than you may have purchased. And how big is the team that you want that's going to manage all of these databases? We find that the typical challenges around scalability, hardware costs, licenses, and the effort lead people to choose managed database options, and therefore a public cloud, which provides multiple database technologies, which are all managed for you, makes for a much easier time as an application development team. How so? Think about you wanting to increase the storage for 1,000 MySQL instances, as you would in case you are going to manage an e-commerce site or a hugely popular chat application, right? Here it happens at the click of a button. If you had to provide high availability, which means you need to have at least a couple of nodes across multiple data centers, imagine the setup time that you will take to build such a thing up as well as test it out. Here, again, is just a selection on a console. Automatic backups, the number of times backup configurations haven't been thought about or provisioned for is not funny. And when you are in a regulated industry, you're literally required to maintain 12 years worth of data. In that case, having an automatic backup facility provision for your DBAs becomes a must-do. And when you need read replicas, right? And what do we use read replicas for? We may use them for creating reports, doing analytics, or just providing read-only access to other use cases. It is again a mere click of the button away when you're using a managed service from a cloud service provider. And that proves to be a win-win both for the development teams as well as the DBA and DevOps team. Google Cloud has been named a leader in the cloud database management Magic Quadrant. This comes on the basis of us having both the breadth the enterprise adoption for all of these database services that I've been mentioning so far to you. I'm going to do a quick recap of each of these services so that you can remember which use case maps to which Google service. Cloud SQL, fairly straightforward. When you're looking for a fully managed relational database and want encryption at rest and in motion by default, because everything that we store in Google data centers is encrypted by default, and want an easy way of maintaining these databases both from a backup and high availability perspective, Cloud SQL would be the answer. Under the hood, the use cases it solves for are what you would use MySQL and PostgreSQL or SQL Server. Mostly online transaction processing use cases, like we mentioned earlier, payments, anything to do with that requires transactional consistency or relational retrieval. Okay. When you're looking at IoT use cases, when you're looking at a very high volume of and a high throughput, low latency use case, both on read and write, when you want linear scalability, which means that every time the data volume grows, you don't want to be able to be working on creating these clusters or scaling them. And if you want to do real-time analysis, we recommend Bigtable. Consider AdTech, right, where you're looking at close to 800,000 transactions per second at some points of time. Cloud Bigtable can handle all of that. But remember, it has a very, very simple storage structure behind the scenes. It will not support the complex relationships or the build out of complex applications that you have, for example, in the SQL case. This use case is largely focused on billions of records at a very high throughput for real-time analysis. When you want to retrieve data extremely fast at sub-millisecond latency, you are always going to cache, and the Google option for caching is Cloud Memory Store. These use cases we've seen, you need them, say, for retrieving your shopping cart, or if you've got a very, very heavy dashboard, you may want to cache it on a memory store. Memory store essentially is under the hood Redis as well as Memcache. And the most scalable of our solutions, which is at once serverless and globally consistent, we guarantee 5 nines of availability, which is an industry first for a solution of this type. It can support both relational and non-relational use cases. It provides consistency at horizontal scale. The kinds of use cases that we are seeing are across industries. And if you think of multiplayer games, if you think of inventory management or financial transactions at the scale of payments, you would consider Cloud Spanner. Cloud Firestore, we've already looked at it, where it serves the purpose of mobile application database and works very well with a backend for front-end scenario. So in summary, we have the whole portfolio ranging from classical relational databases provided by Cloud SQL, then going on to provide you with NoSQL options around Cloud Bigtable and Cloud Firestore, providing your caching solution in Cloud Memory Store, and horizontally scalable database, a new SQL option in Cloud Spanner. Most of your use cases that we've discussed today have been about online transaction processing, or they've been about an online access through applications. But we also have a very deep offering in the analytics space by our serverless offering for data lakes and data warehouses known as BigQuery, and that will be for another session. I hope you enjoyed this chat. Thank you.
Thank you so much, Reva, for enlightening us with your wisdom. I'm sure the viewers will apply your best practices in choosing the right databases. With this, we are moving on to another important and very interesting topic, application modernization. Why? We have Akshay Kapoor joining us today, who will help us demystify the topics of running modernized applications on Google Cloud Platform. Akshay is a seasoned cloud architect and an entrepreneur, having worked with multiple hyperscalers as part of his cloud journey. He is a master's in computer science and a hardcore techie. When not working, you'll find him reading about world politics. Well, today we are going to reach out to him and ask how we can make this world a better place using cloud. The stage is all yours, Akshay. Over to you.
Thank you so much, Parul, for this introduction. Good afternoon, everyone. Hi, I am Akshay Kapoor and a customer engineer with Google Cloud. For the next couple of minutes, I'll be talking about running modern applications on GCP. But before we dive right into it, it's equally important to understand the need for running modern apps in the first place. Let's look at the brief history and the evolution of how we have been developing and deploying applications. Of course, this is an overly simplified and a high-level overview of the operating system. It consists of many components, of which the core part is called the kernel, and that is the only part needed to actually start the host machine. Other components and additional features may or may not be needed by applications to run on the host. So what does this mean? The applications at a minimum require the kernel to run, plus some other components which may or may not be needed, and which can also be shared with other applications running on the same host machine. And I'm sure you'd agree that this way of deploying not just leads to a lot of operational hassle, but also the common problem of this application runs fine on my machine. If you haven't said this before to your teams, I'm sure you will probably in the future if you continue with this pattern of developing and deploying applications. Back then, the solution was to package all together and run them on dedicated servers, which eventually led to a few issues like mentioned here. At the same time, hardware virtualization was gaining traction. It allowed the physical infrastructure to be divided into virtual machines, allowing you to share large physical devices as virtual machines. Tools like Chef, Puppet, Ansible make it easier to repeatedly and consistently build your VMs to a given specification, thus allowing you to minimize the difference between environments. It basically allows you to treat your virtual machines as immutable. So instead of rolling out new versions of your apps on the same virtual machine, you create a new virtual machine each time you need to release a new version of your application. Now, this makes it easier to control the exact environment for your application and isolate each application in its own virtual machine. This seems like a vast improvement, but still, there are issues with this model. VMs take up a lot of resources. They virtualize the underlying hardware and thus add overhead. And VM images can be large as they replicate the complete operating system. VMs can be slow to start and it can take close to a minute at times to start a virtual machine. In the meantime, even before the cloud revolution really took shape, Google was looking at other ways of solving the problem of isolating applications. Deploying each app on its own host seems very wasteful. So Google engineers were looking at ways of safely sharing one host with multiple applications. They came up with changes to the kernel that would allow you to create a process and isolate it and impose strict resource limits to it. Google contributed to the community and started using this technology internally for all their applications. This was the start of containerization. And here we are today, deploying billions of containers each week for applications that are used by billions of users across the globe. And if you look at this evolution altogether, the industry has come a long way, and still there is a long way to go ahead. Now that we've understood the past, present, and what's going to be in the future, I want to take a minute to explain the current state of enterprises and how they develop applications. Today, connected digital experiences are powered by applications. Some traditional in nature, such as web or mobile, and others ranging from connected home appliances, connected wearable devices, amongst many others. The pace of change for these applications is often lost. Speed driven by customers' expectation, competition, and market opportunities. On the other hand, back-end systems and the IT organizations come under pressure by the pace of change imposed by these connected digital experiences and the accelerated pace of change of the business. And as such, it is inevitable that apps will have to modernize for the needs and patterns of tomorrow. There's a variety of app modernization strategies when it comes to building services, but it can be broadly classified into three main buckets: service modernization, your application modernization, and hybrid applications. Let's just focus on what really is application modernization. What do we actually mean by modernization? It's a great buzzword, and businesses are all talking about how they want to modernize their systems and applications. But do they even really know what it means? Modernization refers to conversion or rewriting of legacy apps with modern cloud-native technologies and practices for attaining better business agility. Now, there are 7 transformational technologies and practices that make up modern application development. For example, microservices means the flexibility to move at the speed of your fastest developer, which gives you the agility you need. Containerization means repeatable, automatable, and portable applications, which gives you security and consistency and at the same time avoids complexity. Orchestration means intelligent systems that optimize resource utilization, increasing reliability, and minimized IT management to give you the reliability that you need for your systems. And CI/CD, which is continuous integration and continuous delivery or deployment, means shipping code hourly rather than quarterly, which again gives you the agility you need. Open technology means no vendor lock-in and lower licensing costs, giving you the complete portability to move your applications around. And service and API management means focusing on the value add to your organization, giving you manageability, visibility, and the consistency that you need. And this is what we believe the future is going to look like in future. And I'm going to repeat this once again. The future of applications and the infrastructure that they run on is created with containerized microservices managed through a declarative system with a single control plane experience that uses a service mesh to span all application locations. Now, let me demystify that for you. A declarative system is a system where code represents the final system state. An example of a declarative system would be infrastructure as code, where YAML is used to describe the configurations of hardware and software components, which an automation server then implements. Kubernetes is similar. The developer decides, for example, that a container should be able to auto scale to 5 copies, and then Kubernetes ensures that it happens. A service mesh is configurable, low latency infrastructure and ensures that communication among containerized and often ephemeral application infrastructure services is fast, reliable, and secure. With Google's commitment to open source, we realized the need for new cloud native technologies which will all come together to solve the problem of developing, deploying, managing, and most importantly, securing cloud native applications. And to use the same set of open source technologies I presented in the previous slide, you could leverage these managed services on Google Cloud across the board. Right from analyzing your current stack with DORA assessments to give you insights into patterns and techniques you could use to deploy these applications on Google Cloud. Let me just take a few minutes to explain just a few of these tools and technologies. Some of the challenges that organizations are having as they develop and start using cloud native technologies are having development deployments closely resemble production deployments. How would you containerize code? Understanding what configurations are needed and making sure that debugging services, let's say deployed on Kubernetes, is much more easier. But all of these currently don't have a best practice as such. Developers just want to stay in their IDE and write code. Even without the introduction of all these new tools, technologies, and processes, you'll hear from developers that there are too many distractions keeping them away from writing code. There are an increasing number of tools that are being released to make Kubernetes deployments, as an example, easier for developers. For example, Minikube, Helm, Scaffold, Docker, and of course kubectl as well. With Cloud Code, developers can focus on writing code like they always have and spend less time learning about an endless set of new tools and technologies. Building highly scalable cloud applications is hard, and Google Cloud Code extends your IDE, letting you spend less time learning about the tool chain, configuration, and management of your application, and giving you more time to focus on writing and evolving your code. Now that the code is written, how do you really build these code? Cloud Build is a serverless application to build your apps to create artifacts such as container images, Java archives, and many more to be used in your application. And finally, once you have this, it's time to deploy these in the framework of your choice. Right from leveraging App Engine, which is a fully managed environment, to Cloud Run, which allows you to run your applications on top of a completely managed Kubernetes environment. Cloud Functions, which give you the ability to do event-driven applications. And not to forget, Compute Engine and other deployment targets as well. With that, in summary, I highly recommend everyone to visit this site and do a quick 3-question survey to tell you how mature your organizations are in their modernization journey. With that, I thank you so much for your time and have a good day.
Thank you so much, Akshay, for a wonderful session. Both the sessions complement each other, and I thoroughly enjoyed correlating all the points from both the sessions. Thank you for tuning in and have a great day ahead.